There are three laws that Newton describes motion. Okay. There are three of them. We're really going to go over two of them today. Okay, and I'll mention the third, but we're going to talk about two of them, and we're going to start looking at the math that's involved with the second. Okay, so the first law it's called the law of inertia, and we talked a little bit about this last time, right? You guys introduced inertia in the weight part of the chapter, and we talked a little bit about what inertia means. But the definition of inertia is basically an object's resistance to change, right? It doesn't want to change what it's doing, right? So that the tagline for Newton's first law says, an object at rest stays at rest, an object in motion stays in motion until something acts upon it. Okay, did we kind of talk through that tagline? Right? An object at rest stays at rest, an object in motion stays in motion. And so that means an object is going to move for infinity in a straight line at the same speed unless something acts upon it. So if we were in a perfect physics world, right, and we rolled a ball, that ball would keep going for infinity until it hit something and it moved directions, or it stopped, or whatever it was, right? Even if something caused it to slow down, it would then continue at that slower speed for infinity until something acted upon it, okay? Because in Newton's first law of motion, he's ignoring friction, right? We're ignoring friction. We're ignoring air resistance. We're saying those outside forces, should they be ignored, objects would continue in motion forever and ever and ever. The same thing is true for objects at rest, right? If you're at rest and no one comes to wake you, right, you're going to stay in rest for as long as you can, right? Humans want to follow this pattern too, right? Objects at rest want to stay at rest. Objects in motion probably still want to go back to rest, okay? But they want to not change what they're doing. So an object that's sitting on a table will not randomly start moving, right? There's not something that's going to put it into motion. It's got to be an outside force that does that. So I want to watch this little video about inertia. It's kind of interesting, and it shows you kind of some slow motion, videos of inertia, and it's kind of, it just does a good job of bringing that a little bit more to life. So I'm going to pull that up here, and we're going to try to watch that together. I hope my sound works here.
The law of inertia states that objects will maintain their state of motion unless acted on by an outside force. This means that moving objects will stay moving and still objects will stay still, unless you push or pull on them. There are two safety devices in your car to protect you from the effects of inertia. The first is your seatbelt. When the front end of your car rams another object, your car will suddenly stop or slow down. Because of inertia, your body will want to stay moving at whatever speed it was moving before the accident. If you're not...
Okay, did you hear what that says? Right? Your body is moving 50 miles an hour, right? Because it's in the car, which is moving 50 miles an hour. If the car comes to a stop, a sudden stop, your body wants to continue moving at 50 miles an hour, right? Until something stops it. You see, that's why your seatbelt's so important, right? I'll make this a little plug here for seatbelt safety, okay? But your seatbelt is important because should your car smash into something, your body is going to keep moving until something stops it. It'll be your steering wheel or the windshield or something in front of you if it's not your seatbelt, right? So you can see here in this crash test kind of simulation, the body will keep going until something stops it, right? That's just basic physics. If my car is moving 50 miles an hour, so am I. Right? It doesn't feel like it when I'm sitting in the car, but in all reality, that's what's happening, right? Car's moving, I'm moving. So if the car stops, I'm going to move until something stops it.
Well, this means you will hit a windshield. The seatbelt provides a force to stop your body's forward motion. The second safety device in your car is a headrest. When your car is hit from behind, the car is suddenly pushed forward. Your head will want to stay still, but your body will be pushed forward by the seat. This causes your head to feel like it is snapping back. Your head is actually staying still because of inertia, while the rest of your body is being pushed. Your headrest pushes your head forward with your body so that you don't suffer from whiplash. Look at the difference between a headrest that is properly set versus one that is set too low to push your still head forward.
Okay. So you see how that works in kind of those slow motion scenarios, right? There's lots of inertia, like demonstrations with, moving objects and seeing them fall. But I think seeing them in like a high impact situation is really, it's kind of important, right? That we can see how that law really works and might really affect us, right, from day to day. So, all right, very good. Now, Newton's second law is less about an idea. I mean, it is about an idea, but it's more about the math that goes with it. Okay, so Newton's second law says the acceleration of an object is equal to the net force divided by the mass. Net force divided by mass, okay? And we need to remember here what the definition of mass is, right? We need to remember the difference between mass and weight. Mass is the measure of inertia of an object, and it depends on the amount of matter that it contains. Is mass affected by an object's location?
No.
Is mass affected by what planet it's on?
Yes.
No.
Oh.
Just weight is affected by that. Weight is affected by an object's location. Mass is not. So what's the unit for mass? Kilograms. Write that down. It's really, really important. Kilograms is the amount of mass that is present, and it deals with how much stuff is there. Weight, on the other hand, weight is the amount of how much stuff is there, but also how much gravity is affecting it. Okay, so weight is the thing that changes based on where you're located. Okay, that's a really important distinction. So here, when we use mass, it's got to be measured in kilograms. Okay, so we need to make sure we understand the difference between mass and weight. If it says he has a weight of 40 newtons, that means that that's a weight. If it says that he has a mass of 40 kilograms, that would be mass. Okay, they have a different unit there. This would mean 40 newtons would mean that 40 is equal to mass times 9.8. So his mass would really be something significantly lower than that. Okay, does that kind of make sense? We need to know the difference between mass and weight. Okay, so kilograms is what we're looking for here. Here's the equation for Newton's second law. It tells us the net force of a system, right? Remind me what net force means. The overall, right? When we take this minus this or this plus this, right? As opposite forces get subtracted and forces in the same direction get added. So it's important here. I might even highlight or circle the fact that says F net. That's talking about the net force, right? Is equal to mass times acceleration. Okay, the acceleration of our object. Okay? Do you remember what acceleration is measured in? Remember that one?
Meters per second squared.
Good. Meters per second squared. Maybe write that one down if you're not sure. Mass should be measured in kilograms, and acceleration is measured in meters per second squared. Okay, that's important there. And then what is force measured in? Do you know? What's force always measured in?
Newtons.
Newtons. Good. So put our units on there. That way we know. Okay, force is measured in newtons. Some practice here. Okay. A boy pushes forward a cart of groceries with a total mass of 40 kilograms. What's the acceleration of the cart if the net force on the cart is 60 newtons? Okay. So let's look at our equation again. Our equation is F net equals mass times acceleration. Okay. I'm trying to find the acceleration here. All right. A is my question mark. I know my mass is 40 and it's in kilograms, so that's good. And my net force, they told me, is 60. All right, and so I'm going to go ahead and just plug that into my equation, right? 60 newtons equals mass times A. A is what I'm solving for, right? So how do I get A by itself?
Divide 60 and 40.
I'm just going to divide that over, right? Because it's mass times acceleration. So if I want to get A by itself, I'm going to divide over my 40 kilograms, divide over my 40 kilograms, and I will get A equals this. You'd think I could do that in my head. 1.5? Yes?
Yeah.
6 over 4 is the same as 1.5. Good. Okay, and so that gives me an acceleration of 1.5. And my units for acceleration are meters per second squared. That's important. Okay, make sure you include those units on there as well. Pretty simple, just plugging it in our equation, right? We just have to make sure we know where we're getting those numbers from and we know what we label them with. Okay? All right, next one here. What's the upward acceleration of a helicopter with a mass of 5,000 kilograms if the force of 100,000 newtons acts upward on it? Draw the diagram and include the weight force of gravity. So let's look at what happens here. All right, I'm going to clean this off, give myself a little more room here. So it says I've got a helicopter. Remember, I draw my diagram with a dot. Gravity is pulling the helicopter down. Weight, you call it. Weight is pulling the helicopter down. And we've got a lifting force that's pulling it up, right? When we're talking about a helicopter, we're talking about really all of that air movement, right, is creating a force that pulls that helicopter up. And we know that force is 100,000 newtons. Now, in order for me to solve for the acceleration, let's think about it. I need the net force because net force is equal to mass times acceleration. So what do I have to do first before I can solve the net force?
Put the weight and the upward force together.
Right, I need to figure out what the weight is. Okay, so how do I figure out weight? Do you remember the equation for that?
Mass times gravity.
Mass times gravity. Okay, we're putting those two sections of our chapter together, right? We talked about weight, we talked about net force, now let's put them together. So the weight of my helicopter would be 5,000 kilograms times 9.8. And so my weight would have a value of 49,000 newtons. So first, let's ask ourselves, is the upward force enough to get the helicopter off the ground?
Yes.
Yeah, it's greater than the weight force, right? 100,000 is more than 49,000. So it's going to be lifted off the ground. That's important. Now, if I want to find the net force, am I going to add these two together or am I going to subtract them? I'm going to subtract them. How do I know that? That's right, opposite directions. So I'm going to take 100,000 minus 49,000 and I will get 51,000 newtons. That would be my net force. So then I'll come over here and say net force is equal to 51,000. My mass is still 5,000 and I'm going to solve for my acceleration. And that means my acceleration is equal to 10.2 meters per second squared. Right? A car has a mass of 1,200 and an acceleration of 3. Now, this is a simple problem, right? Do I need to draw the diagram or anything?
No.
Nope. I'm just going to look at my equation that says net force equals mass times acceleration. And I'm going to go ahead and just plug my numbers in, right? I'm solving for the net force. I know my mass is 1,200, and I know my acceleration is 3, which means my net force is 3,600 newtons. Agree? Right? Simple enough? Yeah, sorry, Olivia.
So for the meters per second, how many we do with 3?
This is the unit that goes with acceleration. So the squared part of it is just for the unit. It doesn't have to be applied to the number itself. Yep, good question. Okay. All right, let's look at the next one here. A 25 Newton force accelerates a boy in a wheelchair at 0.5 meters per second squared. What is the mass of the boy in the wheelchair? Okay, so we have a force and we have an acceleration. So net force equals mass times acceleration. All right, my force is 25. My mass is what I'm solving for, and my acceleration is 0.5. And so my mass is 50 kilograms. Okay, during a crash test, an airbag inflates to stop a dummy's forward motion. So just like we saw in that video about that crash test dummy moving forward, this airbag is what stopped it this time. It has a mass of 75. If the net force is 825, what is the acceleration of our object? Make sure we're putting units on those as well. Okay, is that what we had? All right, very good. Last one here that I want to try brings in just a frictional force. Okay, we talked a little bit about friction last time. Tell me, what has to be true about friction? What direction does friction go? Right, opposite of our motion. So friction opposes the motion. So this says a box is being dragged with a force of 100 newtons. If the friction between the box and the carpet is 30 newtons, what's the acceleration of the box? So if you want to draw the diagram, you can. Right, here's my box. It's being dragged with 100 newtons and it's positive. So we just assume it's going in the positive direction. And friction is opposing that with 30 newtons. So you can draw it, but you don't necessarily have to, right? If you feel comfortable doing the problem without drawing it, that's fine too. But the first step I have to take is to find my net force, right? And so when I'm looking for my net force, what am I going to do? Am I going to add those together or subtract them? Subtract them. So I'm going to take 100 minus 30, and that means my net force would be equal to 70 newtons. Okay, and so now I can take that number, 70 newtons, and say 70 newtons is equal to my mass times my acceleration. And that means I get an acceleration of 4.67 meters per second squared. Okay, that feel okay? So some of these problems might take you 2 steps, right? If you have to find the net force first, then you go through and solve for acceleration. That means you've got to do it in 2 different steps.